Today we'll take a look at drift and diffusion. These are two mechanisms which carry current, which allow current flow in a semiconductor. So current mechanisms, let's take a look at the current mechanisms. A change in motion is enabled by some force acting on a body. This is simple Newton's law, we know that from classical mechanics. This force can be an external force or a force created by concentration gradient. External force, for example, if you have a static body and you push it from outside on a level playing field, on a level surface, the body moves. That's the example of an external force. The same thing on if you arrange a set of balls, let's say in a heap, you see that the ball actually starts moving towards a lower concentration gradient. That is this concentration gradient. We'll see examples of these as we go along. In addition to it, if the moving particle has a charge associated with it, then a current flows. We know the current is nothing but rate of flow of charge. So these external forces act on a body which has a charge and the body moves, then a current flows. By convention, current flows in the direction of a positive charge. For example, a proton. If a proton goes from left to right, the current flows from left to right. So the proton moved here from left to right. The current also flows in that direction. Current flows in the opposite direction of flow of a negative charge. For example, an electron. If an electron moves from left to right, the current flows from right to left. The current that we have chosen here are actually conventions only. Almost everybody follows these conventions. You could also have the opposite, because there is the current is just a way of saying the positive charges moving in the same direction and negative charge moving the opposite direction. But you could have the other way around. But everybody uses this, so we'll also stick to it. So let's talk about diffusion first. Assume a fine sand heap, like you would have seen construction material coming. You have seen houses being built and they bring a pile of sand and they put it from the tractor, right? You see it coming as a heap initially, right? It just they dump it and then there is a heap formed. You can see there is a concentration gradient along this path, right? So because of the concentration gradient, the particles tend to move towards the lower concentration. Movement due to the concentration gradient is called diffusion. Okay? There are more particles here and there are less particles here. You'll find particles moving from more particle to the less particle. If there is no opposing force, finally they will all come to this state where everything is equal. But in some cases there will be opposing forces. In this case, in the sand example, the frictional forces opposes the movement. Gravity pulls it down, but there is a frictional force which opposes that movement. You can see that the sand actually goes down slowly, and at some point the movement stops, even though there is a concentration gradient. Why does this happen? This happens when the frictional force is equal to the concentration gradient force created force. There's a concentration gradient here, so particles should ideally move, but since there is friction opposes this movement, hence at some point it will stop. You remember you saw it from here and now it has stopped here. If the frictional force was not there, as I said before, they'll all come to the same equal, there will be no concentration gradient at the end of it. But since frictional force is there, at some point it will stop. Right. Now let's take an example, area. Right. Let's take a cross-section area here. Let's just observe it here. Right. A rate of flow of particle through this cross-section, right, is proportional to the negative of the charge concentration. So the charge flows in the direction of lower concentration. That's why the negative comes. Okay. So dp by dx in this direction is negative. Charge flows in this, the particle flows in this direction. Hence, the rate of flow through this cross section is actually proportional to minus of dp by dx. Okay. Which is equal to minus, since it's proportional, we'll call that proportionality constant d, and that d is actually the diffusion constant. So this has to be experimentally determined for in the case of sand. If for other examples, there's a way to derive this, but we'll see that later. Okay. But the rate of flow of particle through this cross section is minus d dp by dx. And rate of flow of the particle is nothing but dp by dt. What happens if instead of sand we had charged particles? So when a charged particle moves, we know there is a flow of current. We've seen that before. Okay. When a charged particle, they constitute a current. Since concentration gradient causes movement, a current flows. This is important, right? A current flows because there is a concentration gradient. So J is dq by dt, where J is the current density. Since we will take a unit cross section area because we don't know how wide the sand particle or the concentration gradient is, we'll just take a unit area and say that J is proportional to dq by dt, but dq is the amount of charge that goes through the unit area that we saw before. So if the particle is a whole, then Jp, right, the J subscript P, which means the whole current, density of the whole current is Q dp by dt. Q is the charge of the whole. Dp by dt is an amount of hole that flows through the unit area. It's nothing but minus Q dp by dx. Dp by dt, I'm just substituting with minus dp by dx. Since it's a diffusion for the whole, I'm just putting d subscript p. If particle is an electron, then Jn is minus of q dn by dt, because electron has a charge of minus q dn by dt, which happens to be dq d subscript n dn by dx. So I'm just substituting dn by dt as minus dn d subscript n dn by dx, just like what we saw in the sand example. So you can see that Jp has a minus sign. So as the current flows in the direction of lowering concentration, lowering whole concentration, hence this minus sign comes. A Jn, the current flows opposite to the direction of the lowering concentration, hence the Q doesn't go, hence the negative sign is not there. Total current density is Jp plus Jn, these two. The total current, both the particles with a given concentration gradient, both of them are there, then it is Jp plus Jn, and you just add them up. So it's this plus this. Since it's a negative, it's just the minus sign comes out there. So this is your diffusion current. So if you know the concentration gradient at any given time and you know the diffusion coefficients, you can calculate the diffusion current. That is the diffusion. Let's take drift, for example. Before we get into the actual drift, we'll take an example, try understanding what it means. Let's take a street, and let's say it's a market space, and there are shops here. This is the street, marked between these two black lines here, and this is the street here, and there are shops. Forgive me for my drawing, but let's assume each of these is a shop. And there are people who come to shop in the street. You can see that the shops are actually fairly uniformly distributed. There is no there's no concentration of shopping in any one particular area. There are 4 random people. I've just taken 4, but you can scale it up to 100, 200, whatever it is. But since I can't draw so much, I just drawn 4 here for your convenience. And they go for shopping. Right? And each person has his own choices. They go around shopping to the various shops. Since there is no preferred shopping location around the place, you can see that they will, on the average, move randomly here and there. Of course, if they are men, they would have just gone away. But let's assume that they are normal people. They do their shopping, and you can see that on the average, they don't move much. Since there is no shopping concentration in any direction. Right? But let's say now I skew it. This is the original shopping, and I just skew the shopping concentration a little bit towards the right hand side. Right? There are more shops here than here. Right? And we set the same 4 people and let them go do their shopping. Right? Since there are more concentration of shops around this corner, in general there will be a tendency for the people to move towards the right side. You can see that they are all started here, right? They all started here, but there is a general tendency at the end of it to be a little bit towards the right hand side. That's not that everybody is on the right hand side. It's just a general tendency to be on the right hand side. So for right, so that's what happens, right? So you create a force, you create an attraction in one direction. There will be a general tendency for people to move towards the direction. You would have seen that yourself before, and this is called drift. More shopping to the right pulls people towards that direction, and this attraction, this motion under an external influence is known as drift. So people are drifted on the average from the left hand side to the right hand side. So instead of people on a shopping street, now let's assume we have the people replaced by charged particles and shopping attraction by electric field. So coming from the shopping example to our area of interest is charged particles in the presence of an electric field. Charged particles will move due to the electric field, and when they move, a charged particle moves, we've seen that a current flows. Let the direction of the electric field be from left to right as shown here. A hole or a positively charged particle will move in the direction of the field. If a hole moves in the direction of the field, the current is also set up in the direction of the motion of the positively charged particle, in this case from left to right. We call this current density as J subscript P. J stands for current density, P represents that it is because of the motion of a positively charged particle. How about an electron or a negatively charged particle? A negatively charged particle will move opposite to the direction of the field. It in fact moves towards higher potential, from a lower potential to a higher potential, which means it's moving opposite to the direction of the electric field. What about the current? We've seen that the current actually is in the opposite direction of the movement of the negatively charged particle. So it moves in this direction, in this case from left to right, hence in the direction of the electric field. So the current is flowing in the direction of the electric field, while the particle, the negatively charged particle, is moving opposite to the direction of the electric field. So you can notice, before we go here, you can notice that the current due to the positively charged particle and the current due to the negatively charged particle both are flowing in the same direction, though the particles themselves move in opposite direction. I hope this is clear to all of you. Now the current itself is given by this formula, Q times N times V. This we can actually derive by knowing that the current is nothing but the amount of charge that moves per second across a given cross-sectional area. So let's say the average velocity, V is the average velocity. In fact, it's called the average drift velocity. If V is the average drift velocity, okay, all particles within V meters of the cross-section will move through the cross-section in 1 second. I'll repeat that again. Let's assume there is a cross-section somewhere and there is a direction. Let's say the cross-section is here and the particles are moving this direction. All particles within V meters of it, where V is the average velocity, will have moved through this cross-section in 1 second. Okay. So the number of particles per unit area then becomes N times V, where N is the number of particles per unit volume. So the total amount of particles then becomes N times V, and the charge, if the charge associated with each particle is Q, then it becomes Q N V. We have seen this before. So this is the amount of current that is flowing. So in our particular case, the total current is J due to the positive charge and current density due to the negatively charged particle. It is N times Q times N mu N plus P mu P E. Basically, we are replacing velocity by a term mu times E, where mu is called the mobility, and we'll see that next. So in this case, mu n is the mobility of the electrons and mu p is the mobility of holes. So velocity we just represent by this factor mu times e, and we're just adding up the two currents. So we'll just take a look at what mobility means. In the presence of an electric field, charged particles experience a force. This is basic electrostatics, we know that. Force leads to acceleration. So if you have a body and you keep applying force on it, it will accelerate. If there's no opposing force, velocity will increase, right? Increasing its velocity. So even a small field, will it tend to infinite velocity? So let's take a classical mechanic. Let's say you have a body at rest and you start applying force on it. If there is no friction, there's no opposing force, ultimately, because there's an acceleration, velocity will have to reach infinite. Of course, there's a limit on velocity because of speed of light, but let's assume it goes to an extremely large velocity. Right? So in this case, so if there's an opposing force, what will happen? The body will tend to saturate at some point and say, okay, acceleration beyond a certain point will come back to zero. Okay? Let's say, for example, a frictional force comes. Frictional force depends on the velocity, and as the velocity increases, let's say the frictional force increases. So at some point, the frictional force will be equal to the applied force, and hence no more acceleration, hence the velocity will saturate. Okay. In an electric field, instead of friction, there are collisions with atoms and electrons in the lattice. So an electron will accelerate from zero, let's say, accelerate in the direction of the electric field, or opposing to the direction of the electric field. It gains velocity, but as it gains velocity, it comes and collides with atoms in the lattice. It loses its energy, hence its speed, right? And then again from that speed, again it will start accelerating because of the presence of field. Again go and collide with an atom, again lose its energy. So it keeps doing this. So at some point the velocity will build up, but after some time, the collisions with atoms, because between atoms and electrons, will tend to saturate the average velocity. So this collision is acting as an equivalent of friction for classical mechanics, in classical mechanics. Let's say the E field is in this direction, from left to right, okay? In this direction, let's draw the graph of the electric field versus velocity. So for small e, velocity is mu times e. That is, the velocity is actually proportional to the electric field. Remember, it doesn't go to infinity because of these collisions. So velocity is proportional to the electric field, and you can see it's fairly linear. This proportionality factor is called mu, which is called the mobility. For very large electric fields, V actually tends to saturate out. This is due to complete loss of energy in collisions between the two atoms and the electrons. So it tends to saturate out at very large electric fields. So here you can see, though the electric field is applied, the average drift velocity is not changing. For medium E, that transits from here to here. Does it mean that every electron goes in the same direction as others? No. Remember we talked about the people. They were going randomly in the street, but they were generally tending to drift in the direction of the presence of more shopping. It's not that everybody just went directly to the presence of more shopping, right? They went to 10 different places. They were randomly moving, but the average movement was towards the more shopping area. Same way, an electron or a hole don't move in the direction of the field applied. They all will move randomly, but on the average, they'll move as dictated by the electric field. This is important to know, because not that every electron moves in the same direction. Right? On the average, if you take a large number of particles and take their average velocity is the average distance traveled by the average time, then it is in the direction of the electric field, or opposing to it, depending whether it's a hole or an electron. So mu depends on this mobility factor that we saw, depends on doping density in a semiconductor, on the base material, because this defines this lattice structure, and the temperature. We'll not define the relationship right now, but just remember that it depends on all three: doping density, base material, and temperature. So you need to know all these three to know the mobility. We'll take a look at it. Let's assume the base material is silicon. Let's assume the temperature is 300 Kelvin. Right? So this is a graph which I've taken from a book, which is a table, sorry, not a graph. It's a table which I've taken from a book, which tells me the mobility of an electron in silicon at 300 degree Kelvin if it was if it was uh, if it was doped with arsenic, phosphorus, or boron. So I said electron. In the case of boron, it is a hole. Depending on the type of doping material, you will either get a hole or an electron. With boron, you get a hole. So arsenic, phosphorus, or boron are the doping material. So we know the temperature, we know the base material, and we know the type of dopant. Right? So depending on the concentration of the doping that has been done, you can see that the mobility changes. Right? These values here are the mobilities. So for example, if the doping density was 10 power 15 atoms per centimeter cube of arsenic in silicon at 300 degree Kelvin, then the mobility is 1359 centimeters square per velocity second. If it is 10 power 17 with phosphorus in silicon at 300 degree Kelvin, then it is 721 centimeters square per volt second. You can see as the density of the doping increases, the mobility actually falls very clearly. Okay. So more the density of the doping material, lesser the mobility, because there is more chance of collision and more chance of energy loss. Right? Whichever way it is, whether it's phosphorus also you can see that happening, with boron also you can see happening. Right? So as you increase the density of doping, the mobility reduces. Fairly dramatic, almost 6-7 times. You can see it here. It's in fact here more than 10 times here. Right? Also notice that the mobility of an electron is much better than the mobility of a hole for the same doping density. So these two are electron contributors. You can see they're almost the same. Right? Across them they're almost the same. But mobility of a hole is much lower. And we know this why. Right? Takes much more energy to dislodge a hole from the bond and make it move. So the mobility of a hole is much lower. Almost 3 times or 2.5 times lower. Right? So let's take an example. Let's say silicon is doped with 10 power 15 atoms per centimeter cube. Right? Let's say the dopant is arsenic. So arsenic is here. So we'll have to pick up 1359. Mobility is 1359 centimeters square per volt second. Right? So this 1359 is appearing here. Right? Now let's say silicon is doped with, on the other hand, 10 power 17 phosphorus at 300 degree Kelvin. So since temperature fixed in this case, it's actually is mobility is right. That's correct. It's 721. Right? 721 centimeters square per volt second. Arsenic and phosphorus are donors, as we said, and boron is an acceptor. Right? And we can see that mobility of electron is more than mobility of all this. So let's look at conductivity. We've seen that the current density is nothing but the current due to the holes or positively charged particles, and current due to the electrons or the negatively charged particles. We've seen that is given by Q times N mu N plus P mu P times E, where E is the electric field. This is the drift current. So this is the total current when there is no carrier concentration gradient, because this contributes the diffusion current, and there is no diffusion current. Current is given only by the drift current. Now conductivity, the sigma represented by sigma, is the ratio of the current density to the electric field, which is nothing but Q times N mu N plus P mu P. Resistivity is reciprocal of conductivity. Straightforward, right? So this just gives you the resistivity of a piece of semiconductor which has N electrons, free electrons, and P free holes. Remember, what is resistivity? Resistivity, the total resistance of a block is given by rho times L by cross section area, L by A, rho times L by A. It is that rho that we are trying to calculate out here. So if you know the doping concentration, you know NNP in silicon at a given temperature, you know NNP, and you can find mu1 and Vp from the table before that we have discussed. So if you can calculate the resistivity, and once you know the resistivity, given the physical dimensions of the semiconductor, you can substitute in rho L by A to find out the resistance or the conductance of the block. Okay. So this is just a question for you to practice. A piece of silicon, so we said it's a silicon substrate with arsenic, and I've given you the doping density, and I'm giving you the physical dimensions: 100 mm long, 10 mm wide, and 1 mm thick. Okay. Just remember, I've given you in mm, whereas ND and the mobility were in centimeters. So just make sure that you get the right units correctly there. I just wanted to calculate the resistance when contact from each end. Take the mobility from the table listed in the previous slide. We've seen that what happens when ND in silicon at 300 degree Kelvin, assume 300 degree Kelvin here, we know the mobility. Okay. Since you know ND, you know N, and you also know P. Okay. But just think a little bit about it. P is extremely small, so what can you do with it? Right? Do you need to even consider it? Okay, just calculate and see what happens. Your answers before. Short summary: doping changes the concentration gradient by orders of magnitude. You've seen that in the previous lectures. P-type doping, majority carriers of holes, and N-type electrons. Just to reiterate, current is due to drift, a movement of charged particle due to an electric field, and diffusion, movement of charged particle due to concentration gradient. This is the two things that we saw in this chapter. Drift is due to the presence of an electric field. Diffusion is because of the concentration gradient. Both are responsible for current conduction. Mobility of charged particle depends on the base material, temperature, and doping concentration. Okay, so we have done the discussion now on drift and diffusion. Drift happens when there are free charged particles in the presence of an electric field, and diffusion happens because of a concentration gradient. I hope these two concepts have been clear to you. Okay. So before going to the next lecture, I would like you to discuss the following topic among yourselves. Okay. I would sincerely urge you to go through it very carefully, discuss among yourselves, so think independently. Because if you do that, the next chapter becomes that much more easier to understand. Let's assume that we have created an electron concentration gradient in an N-type semiconductor. Okay. How to create this electron concentration gradient, we'll tell you later. Okay. But assume that somehow we have created it. So let's assume that the electron concentration gradient on the left hand side of the semiconductor is more than on the right hand side, and let's say it exponentially decays from the left to the right. The question is, what will happen over time, and what is needed to hold the carrier concentration? The real question is, if I started with that kind of gradient, will it stop only when all the electrons have become uniformly distributed, or will it stop somewhere in between because of an opposing force that's created? These are questions that we need to answer. Just think of the parallel with the sand example that we talked about, when you created a heap of sand, it started flowing and then it stopped somewhere in between, right? Just go back to that example and see what should happen. Okay. Also, check out what happens if the electron concentration gradient was replaced by a hole concentration gradient. Okay. The only difference between these two is that the charge of the particle is positive here and was negative here. So something has to be different. Just consider these two cases, because when we start looking at the PN junction, which is the topic of the next chapter, if you understand what happens here, that chapter becomes that much more easier to understand. Okay? If you understand that, the basics of PN junction is almost done for you. Okay? So please do discuss and give it some thought. I'm sure there are going to be some counter views and counter views. Discuss it, and then we'll discuss it in the next class.